Today we're going to start chapter 3. I'm skipping chapter 2 because I don't think it's that terribly important. It's just like scientific notation and significant figures and things that you probably studied already. If not, it's not really that big a deal, and I want time for other things. So this video is going to be on basically the background on how the subatomic particles were, discovered, and how you go from a philosophical idea of the atom to a scientific theory. When you crush a lump of sugar, you can see that it is made of many smaller pieces of sugar. You may grind these particles into a very fine powder, but each tiny piece is still sugar. Now suppose you dissolve the sugar in water. The tiny particles seem to disappear completely. Even if you look at the sugar water solution through a powerful microscope, you cannot see any sugar particles. Yet, if you were to taste the solution, you would know that the sugar is still there. Because, what's the evidence for that? It tastes sweet, therefore indicating that the sugar is still there. Observations like these led early philosophers to ponder the fundamental nature of matter. Is it continuous and infinitely divisible, meaning you can keep making it smaller and smaller and smaller forever? Or is it divisible only until a basic, invisible particle that cannot be divided further is reached? So we start with this dude who was back in ancient Greece. His name was Democritus. The particle theory of matter was basically kind of come up with by this guy. He called nature's basic particle an atom, which comes from the Greek word atmos, which means indivisible. So he was the first one to kind of say that all matter is made of individual particles that cannot be divided. The next guy up, who looks basically the same, although it is a different guy, I promise, his name was Aristotle. He's one of the world's most famous philosophers. You have to remember that back like 2,000 years ago, we're talking like, what was it, 500 or 400 BC? So like the year -500. Science and philosophy were basically the same thing. Philosophy being nowadays kind of like, why are we here? What's the purpose of life? Just kind of contemplating life's big questions. And so that's what these guys did. They just kind of sat around and tried to figure things out. And a lot of our fundamental ideas of science came from philosophers. Anyway, Aristotle was part of the generation that succeeded or came after Democritus. His ideas had a lasting impact on Western civilization, and he did not believe in atoms. He thought that all matter was continuous, and his opinion was accepted for nearly 2,000 years. Neither the view of Aristotle nor that of Democritus was supported by experimental evidence. Remember, I just said a bunch of philosophers just kind of sitting around thinking about stuff and coming up with ideas saying, oh, I think it might be like this. So each remained speculation, meaning just kind of ideas and not real scientific basis, until the 18th century. That would be the 1700s. Then scientists began to gather evidence favoring the atomic theory of matter. So for 2,000 years, basically, it was just a bunch of dudes sat around and thought about what stuff is made of. Nearly all chemists in the late 1700s, again, that's the 18th century, accepted the definition of an element as a substance that cannot be broken down further. At this point, we already knew about chemical reactions, but there was a great disagreement as to whether elements always combine in the same ratio when forming a specific compound. Now, there's going to be 3 laws that are associated with the foundation of atomic theory. Like I said, a law is very rare in science. That means that it has been backed up by so much evidence for so long that it is 100% truth, no longer to be debated. The first one is called the law of conservation of mass. I'm hoping you already know what this is. With the help of improved balances, investigators could accurately measure the masses of elements and compounds they were studying. This led to the discovery of several basic laws. Like I said, the first one is called the law of conservation of mass, which is that mass is neither destroyed nor created during ordinary chemical reactions or physical changes. So you can see based on this animation that you start with sodium bicarbonate and acetic acid, and together they form a mass of 243.68. As the reaction occurs, mass does not change because atoms don't just disappear into nothing, and atoms are not created out of nothing. The next law is called the law of definite proportions, which says a chemical compound contains the same elements in exactly the same proportion by mass, regardless of the size of the sample or the source of the compound. That's a complicated way of saying, like giving an example, salt. Salt is made of sodium and chlorine. The percentage by mass of sodium to chlorine is 39.34% sodium and 60.66% chlorine by mass. And that is going to be true of salt no matter how big of a sample size you have or where the source of your sample is. That means like salt is salt is salt is salt. It has the same proportion of elements by mass. The third law might be the most confusing one to understand. It's the law of multiple proportions. So first, we have to recognize that two elements can sometimes combine to form more than one compound. For example, carbon and oxygen can form two different compounds. It can either form, carbon dioxide or carbon monoxide. So this is carbon monoxide, carbon dioxide. So we're going to consider samples of each of these compounds that contains 1 gram of carbon each. Okay. In carbon dioxide, if you have 1 gram of carbon, you're going to have 2.66 grams of oxygen. Remember, that's the law of definite proportions. Like every compound has exactly the same percentage of elements by mass everywhere in the world. So for carbon dioxide, if you have 1 gram of carbon, it's going to combine with 2.66 grams of oxygen. Carbon monoxide with 1 gram of carbon is going to contain 1.33 grams of oxygen. So the ratio between 2.66 and 1.33 is 2 to 1. So that is when two elements can combine to form different formulas, the ratio between the element in one compound to another is always a small whole number ratio, like 2 to 1, 3 to 1, something like that. So if you're looking at carbon and oxygen, the ratio of oxygen in CO versus CO2 is 1 to 2. That's multiple proportions. Okay, then we get to John Dalton. He proposed an explanation for the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. He reasoned that elements were composed of atoms and that only whole numbers of atoms can combine to form compounds. His theory is summed up in 5 parts. Whoa, no, I don't want Siri, go away. Number 1, all matter is composed of extremely small particles called atoms. Okay. 2, atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. This is where he starts to go wrong, but I'll talk about that later. Number 3, atoms cannot be divided, created, or destroyed. Number 4, atoms of different elements combine in simple whole number ratios to form chemical compounds. And number 5, in chemical reactions, atoms are combined, separated, or rearranged. This is the basis for atomic theory. He was the first one to kind of come up with 5 what we call postulates or assumptions about matter. So Dalton turned Democritus's idea into a scientific theory that was testable. This is what the difference between a bunch of guys sitting around contemplating life and matter in the universe versus actually putting together a theory which you can then test and gather evidence for. Not all parts of his theory have been proven correct. For example, we know that atoms are divisible into even smaller particles, And we know that elements can have atoms with different masses. So for this one, we know that we can split atoms. That's what the hydrogen bomb does, is that you split an atom and huge amounts of energy is released. We also know that atoms are made of smaller particles, the proton, the neutron, and the electron, and those parts can be manipulated and changed. And for the second part, we know that an element can have atoms with different masses. These are called isotopes. An isotope is an element that has a different number of neutrons, therefore different masses. For example, hydrogen. There are 3 isotopes of hydrogen. There's hydrogen 1, hydrogen 2, hydrogen 3, or hydrogen, deuterium, and tritium. So all of these are the same element, therefore they all have to have the same number of protons, because remember from the previous lessons, what identifies an element is the number of protons in the nucleus, so they have to have a proton. Electrons, we basically disregard their mass because it's so minuscule, it's so minute, it's so small that we don't really count it towards the total mass of the atom, which means that the mass of the atom comes from the proton and the neutron. So for hydrogen, it has an atomic mass of 1. It definitely has to have 1 proton, which means it has 0 neutrons. So this has 1 proton, and 0 neutrons. For deuterium, it has a mass of 2. Again, it has to have 1 proton because it's hydrogen, but to make up for the mass, that means that it has 1 neutron. And for tritium, again, we have to have 1 proton, but to make up for a mass of 3, we have to have 2 neutrons. These are isotopes. You can remember the trick that isotope, the P, means they have the same number of protons, which means the neutrons are different. So these are the problems with Dalton's atomic theory.